You missed the weekend. Well, the next weekend is only 5 days away, so we'll get there, okay? All right. Well, I hope you guys are doing well. And have you guys taken a look at the homework? Yes. Some of you, yes, but because it's not due till next Monday, some of you no. Okay. That's always the thing, right? So I try to give you ample time to complete, but the understanding there is that you will also use the time given to work. So, but I get it. You know, I was procrastination was always my weakness. So, yeah. Well, we all have many weaknesses. All right. Okay. So today, let's see what we will cover. We're going to cover rejection, acceptance, rejection. It's like the story of our life. 102. Okay. All right. Okay, so we're looking at acceptance, rejection, sampling, or let me change. I just want to use the black pen here. Also called just rejection sampling, if. So we're still in this, well, a lot of Monte Carlo methods is all about trying to get random samples from a particular distribution, okay? So last week we covered inverse transform methods for getting random samples from, you know, a particular distribution. On Friday, I went over the Box-Mueller transform, and I didn't finish, so I've asked your TA to go over Box-Mueller in section tomorrow. So that will happen tomorrow. And you know, this is still just another way of drawing samples from a distribution. Okay, so acceptance, rejection, sampling. Okay, so this is just another method to get random samples from a distribution. And this is the idea here. Okay, you have some distribution which we call, what is the letter we have? We call some distribution F, okay, with a PDF. Okay, so you know, we want to get samples drawn from a distribution F. Okay, but F, maybe this is complicated. Okay. So what we do, so instead, we draw a random value from G, okay? So G is just another distribution. G is another random distribution that's easier to sample from. Okay, and the only requirement, okay, G does not have to look anything like F, but the only requirement is that G and F have the same support. So the support means where F is not equal to 0, then G also cannot equal 0, right? So if if f is defined from negative infinity to positive infinity, then g also has to have non-zero values from negative infinity to positive infinity. Or if f is from 0 to positive infinity, well, basically the support of g has to be bigger than the support of f, or the support of f has to be a subset of the support of g. Okay, so the support of f, so support is where the function is not 0, or in this case is greater than 0. The support of f has to be a subset or fully or equal to the support. All right, stop that now. Equal to the support of g. Okay. All right, and then so what do? We draw a random value from g. Now, how do we get the random values that we get from g to represent random values drawn from f? Well, this is where the rejection part comes in. Okay, we just figure out the ratio between f and g multiplied by some constant. Okay, so we figure out the ratio between f and g so instead we draw a random value from g. Okay, so this random value we're going to call y. The value drawn is y. Okay, so we figure out the ratio between f of y divided by g of y, and then this is also we'll generally multiply this by some constant m. Okay. Some constant m, and then we draw a uniform value, and if that uniform value is smaller than this, we'll accept it, and if it's not, we reject it. Okay, so again our ratio is f of y divided by m times g of y. Okay, and then we draw u, a value from the random uniform, (0, 1). And if u is less than this ratio, is it less than or equal to? Yeah, less than or equal to the ratio, we accept the value y as a sample, x drawn from f. And if u is greater than the ratio, we throw away the sample. Okay. And that's the accept reject method. Okay, technically we could stop here and be done, but this probably makes no sense, right? It's just like I just wrote a bunch of stuff on the screen. I don't know, maybe it makes sense. Okay, let me try to illustrate how this thing works. Okay, so I'll let you guys finish writing. Okay, so let's say I want to draw from, let's say f is going to be the beta distribution with shape parameter 2, 2. Okay, f is beta 2, 2. I think, what is that? Let me just look this up here. All right, Wolfram Alpha, I need your help. Beta distribution. Oh, you don't give me the functional form? Rats. Okay. I want to say, let me just, is this equal to, I apologize, x times x minus 0.5, and I want to say, is it 1/6? Or is it 6 times this? Let me just check this. I think this is -6. Okay, let me just check this. Integral of this dx from 0 to 1. If this is equal to 1, then this is the it's not right. Oh, sorry. Shoot. Okay. I don't remember the functional form of this. All right. Let's just do something simpler then. Sorry, because I can't remember what it's just an upside down parabola, but I can't remember the constants off the top of my head. Okay. All right. That's fine. Let's say. Let's say we have this. Okay. And this, let's say we go from 0 to 1, and this goes up to, so at 0.5, and so the total area here has to equal 1, right, for it to be a PDF. And so on this side we've got y is equal to, I believe, 2x, no, is it 4x? 4x will take me 4 times 0.5. No, 2. This is, it's 2x, and then for 0 is less than x less than 0.5, and then, or am I doing this wrong? Why am I? It's 4x, right? 4x, and then on the other side it would be 4 minus 4x. Is that right? Okay, and so what we're going to do, and this has a max height of 2 here, right? You have a question? No. Okay. All right, so this is let's say this is our PDF here, okay? And okay, so we want to somehow generate random samples from this distribution. What do? What we're going to do is, let's say we don't know how to draw samples from this. So we're going to just draw a y coming from uniform 0, 1. And maybe I should have picked a different thing, okay? So when we do this, okay, so we draw y from 0, 1, and then let's say the y that we end up drawing comes from right here. Okay, this is the y that we get. So let's say, you know, y is equal to, I don't know, 0.9 or something like that. And we want to know, should we accept this, right? Should we accept this, yes or no? Okay, well, what we do is we pretend like we're going to create a, so the uniform distribution, this thing looks like this, right? It goes from 0 to 1 with a height of 1. And what we do is we just multiply this thing by a constant, okay? And so here, because this thing has a max height of 2, our constant m is going to be 2, okay? So m is equal to 2, so that when I multiply this thing by 2, it ends up going from 0 to 1, and now with a height of 2. Okay? And so if I superimpose my modified uniform, okay, this is what it looks like. Okay? And right now I've drawn a random value y. And I want to know, well, should I accept this, yes or no? Okay? So what I do is I'm going to draw another value, u, that comes from basically 0, 1, but I'm effectively multiplying it by 2 now, okay? Well, okay, so u also comes from random uniform, 0, 1. Okay, u will come from the random uniform, 0, 1. And then we, and so let's say this value ends up being, I don't know, 0.47, okay? So I draw a random uniform 0.47, and then I just, I say, okay, well, what is f of x divided by g of x times m, okay? So f of x at y equals 0.9, so f at 0.9, my thing would be 4 minus 4 times 0.9, and I get what? What is that? 0.4? Okay. So I get that is equal to 0.4, and then g of x, g at 0.9 is just 1, right? Because it's uniform. So this is g of x. So this is just the uniform. And so my ratio is equal to 0.4. It's f divided by g, 1, times my m of 2. So my ratio is equal to 0.2. Okay. So basically what we're saying is that this height is 1/5 of the distance from here to here, okay? So from 0 up to here, this is, 0.2 of the way, and this is 0.8 of the way. And what we're going to say is we will accept this if my random value is less than 0.2, okay? And it's 0.47, so that ends up in this region. So we throw away this number. Okay, so 0.47 is larger than 0.2. 0.47 is greater than 0.2. So we throw away the proposed value of 0.9. Yes, sorry, this is all garbled here. Okay. So visually, what we've got going on, sort of like this, is you can think of it as, let me just flip to the next slide and draw this a little bit better. Okay. So this is the distribution we want. We want to get, this is what we want to get, okay? Our proposal distribution, after we've multiplied it by a constant, is kind of like this. Okay, and you can imagine, so with the uniform, all of these values show up equally likely, right? What we're doing now is we're practically we're first going to just draw a value at random in this direction and draw a value at random in the vertical direction. Okay, so it's almost like throwing a dart in this rectangle. Okay, and we only accept the dart, and we only accept the x value of that dart if it falls inside the triangle. Right, and so what happens is that the accepted dart throws will form the triangle. Our PDF will form the triangle. So we can say, so first, so we first propose y from the function g, okay, and that's just randomly along here. So it could be right here. So this value should have a pretty high chance of getting accepted. Yeah. So if this is y, and then what we do is we say, okay, well, we're going to look at this, and we're going to say, okay, the ratio between our value of f to the total value of g, f covers about, I don't know, 80% of it or something like that. Okay. So we find the ratio between g of y divided by m times f of y. Basically, m has been multiplied by some constant, and then we say, okay, this in this picture, maybe this is like 82%, and this is 12%. And so we're going to accept this candidate value y with basically probability 0.82. How do we do that? Well, we generate a u from 0 to 1, and if it's smaller than 0.82, we accept it. If it's bigger than 0.82, we reject it. Okay. So in this case, with a probability of 0.82, which is our ratio. Okay, and then so we generate u. If u is less than or equal to 0.82, we accept y. Otherwise, we reject y. Does this kind of make sense as to how we're going to end up getting the resulting distribution? Yes, question?
I don't know if I missed this part. So is M sort of working as like a level of confidence?
No, M is just, so the requirement of PDFs is that they integrate to 1, right? And so unless they are identical, one distribution will always be taller than the other distribution at some point, okay? Because yeah, right? Because you're changing the shape, and so if you're decreasing the area here or decreasing the height in one spot, in order to preserve the total area of one, it's going to be taller in another spot, right? Okay. And so what M does is it just makes sure that the proposal distribution is always taller than the target distribution. Okay, it makes sure that G. Wait, I did this upside down. I'm sorry. It always makes sure that G is taller than F, right? So I'm pretty sure I have it correct on the other slide. I just messed it up on this one. Yeah. Okay, so just make sure that, so this thing is going to, this part is m times, g of y, or g of x, or whatever it is, okay? And so that makes sure that m times g is always taller than the target distribution, and that way, when we talk about the ratio, that ratio is always between 0 and 1, okay? And you can make it arbitrarily tall. You can make it like, this will also work, okay, if the thing was this tall and your function was only down here, okay? This would still work, it's just you're throwing away a lot more points. Okay, this is fine. You can say, like, I want m to be 1,000, okay? This would be terrible for your computational efficiency, but mathematically, in the long run, it will also work out. It's just because you're gonna propose some value, and then you will only accept that value based on the ratio between m times g of y and f of y, okay? So, if m is too big, it's still okay. The resulting distribution works, it's just you will be rejecting a lot more values. Okay, so I want to make sure that conceptually this idea makes sense to you guys. So we have a target distribution that we want. We can't sample from that directly, so we just use some other distribution. In this case, we've been using the uniform because it's very easy to visualize and conceptualize, and we generate a value from there, and then do we accept this value or not? Okay, well, the uniform is going to just, every value is equally likely, and obviously that's not the case with the target distribution. So we just basically see how tall is the target distribution relative to the uniform distribution, and if it's very close, then it will get accepted with a high rate, and if it's much shorter, then it gets accepted with the low rate. Question? Yeah.
So I understand your example where the triangles are acceptance rate, but just to clarify, how would you define m? Like, is m like a value?
So m, ideally, okay, m is a constant that makes the target distributions, like, will basically make the proposal distribution just tall enough so that every ratio is less than or equal to 1. Okay, that's the ideal scenario, and that makes your rejections as minimal as possible. Okay, but if you're not sure, you can always pick a really big m, and it's just you're going to be just rejecting a lot of values. Okay. Yeah.
If we know that f has that certain shape, don't we then know how to sample from it?
No. So you might know the shape of the PDF, okay? But to sample from it requires, it's more complicated, right? We can do an inverse Cdf method, okay? But inverse Cdf requires that we have the integral of that function, right? So if we have the PDF could be this complicated thing, and the inverse Cdf might not be something that we can calculate. Like, we might not be able to calculate the integral, and then we might not be able to calculate the inverse of that thing. Okay, so the integral, the Cdf is the integral of that PDF function, which might not be calculated. And then even if we have the Cdf, we might not be able to invert it either. Okay, so all we need here is we just need to be able to evaluate what f is. So the benefit here, yeah, it's a good question, right? So, benefits of this method. Okay, we only need to be able to evaluate f of x. Okay, we do not need, which is the PDF. We do not need the CDF, okay, which requires an integral. And we do not need to be able to invert the CDF, okay? And we do not need the inverse of the CDF. Okay, which the inverse of the CDF, that works for inverse CDF method, right? You just generate a random uniform, and then you plug that into inverse CDF and you get a random draw from your distribution. Okay. The disadvantage here is that in high dimensions, you do a lot of rejecting. Okay, which means it can take a long time to get a needed number of samples. Yes?
How do you generate U?
How do you generate U? U is just random uniform from 0 to 1. Okay? U is just random uniform 0 to 1. So we're assuming we can generate U. Okay? And this is an example where the proposal G, the proposal distribution G is uniform. Okay? This acceptance rejection method can be used even when the proposal distribution is not uniform. Okay? So let's say, I don't know, let's say you have some distribution that looks like this. Okay? So let's say this is your f of x. Okay? We want a sample from here. Okay? We want samples from f of x. And if this goes off to, let's say, positive infinity and negative infinity, then the uniform is not going to be a good thing, right? Because then you have to say uniform go from negative infinity to positive infinity, and then it has a height that's 1 over infinity. It doesn't work, right? So what we can do is our g of x can just be, I don't know, something like the normal distribution, okay? Something like this. And what we do is we multiply g of x so that it is always taller than f of x. We multiply g of x by some constant m, okay? So we multiply g of x by some constant m so that it's always taller, and I don't know what this would look like, but maybe it looks like, this looks terrible. All right. Just pretend this looks like the normal distribution, okay? So this is now, this is m times g of x, okay, where g of x is the normal distribution. All right, how does rejection sampling work here? It works exactly the same way as before. All right. First, we will draw so we'll say g of x. We'll say g of x is the normal distribution, or is equal to the normal distribution, and then we multiply this by some constant m, so it's g of m times g of x is always taller than f. Okay. M times g of x is always, taller, or as taller than f of x. Okay. All right. So all we do is we just generate a random value from g of x. Okay. So we say, okay, here's a value. All right. So here's a candidate value y. All right, so when you draw from normal, that means most of the values in the middle these values will show up quite often, okay? And then, values out here will show up less often, right? But you might get a value like that. Okay, so let's say we take y. All right, and in this case, we just say, okay, this is now up to 100%, and we say, okay, approximately how much this is f of x, and we say or f of y, and we say how much of this distance is covered by f of y, right? So our ratio is still f of y divided by m times g of y. Is that okay? And so, I don't know, I'm just eyeballing, this looks a little bit under 50%, okay? So I'm just gonna say it's 47%, I'm making this up, okay, based on our picture. And then we say, okay, well then this value will get accepted with a probability 0.47. So we say u comes from 0, 1, uniform 0, 1, that's easy to do. And then if u is less than or equal to 0.47, we accept y. And if u is greater than that, we throw away y, we reject it. Okay. And then we just do this. Over here, we do the same thing. Okay, let's say we proposed some value over here. Let's do it right here, okay? Okay, so this is now my max, and this is now 0.8, okay? And so this will be y2, all right? So we find the ratio of f of y2 versus m times g of y2. And this looks like 0.8, okay? So again, we generate u from uniform 0, 1. And if u is less than or equal to 0.8, accept y2. All right. And that might feel weird because it says, you know, technically if we look at the PDF, this is taller than this. Okay, and we're like, well, shouldn't we accept this value more often than this value if the PDF is taller over here than it is down here? But over here I've got 0.47 versus 0.8. Yes, that's correct, but what happens is because our proposal distribution is normal and it's not uniform, that means these values will get proposed more often and these values are proposed less often. And so everything gets weighted out. So this value gets proposed more often, but it's accepted less often because the ratio between the height of f and g is shorter, okay? These values get proposed less often, but they get accepted more often, okay? And values out here, you know, so, you know, out here, these values don't get proposed very often, and then they get accepted very rarely. So values out here will rarely show up in your sample, okay? You know, values over here, you know, and you can kind of say, like, okay, and these values right in the middle, they're going to get proposed very often, but because the f of x is very short, they get accepted less often, okay? And so this acceptance rejection method, it works because, you know, whatever you pick as your proposal distribution, it will propose values more often or less frequently based on the proposal distribution, and whether they get accepted or not depends on the ratio between your target distribution and the proposal distribution. So everything, it balances out. The book has a brief proof in there, but I feel like we don't have to do the proof to just kind of get an intuitive sense of how the acceptance rejection method works. So we propose values based on the simple distribution, and then we accept them based on whether or based on the ratio between the height of the simple distribution and the target distribution. Is that okay? All right, and so I can't give you previews of what we're going to put on the test. Okay, so let's say we're going to make our PDF, right? So okay, I think what is beta 1.5? 1.5 is like a semicircle. So and I think beta distribution distribution A equal to 1.5, B equal to 1.5. This looks like half a circle. Okay, so this is gonna, what is this? Okay, so here is our PDF. How do I copy this? 1 minus x to the 1/2 and x times the 1/2. All right. So we'll say x is 1 minus x. This will be f to the 0.5 times x to the 0.5. All right. Oops. Function x. Okay, and then we'll do x is sequence 0 to 1. Out, we'll say 101 values. Okay, and so we'll do f of x. Is it length out? Length out is 101, and then so we'll do. So this is technically not correct because if I plot the PDF versus x, the integral is not going to be equal to 1. Okay, so it's technically not the PDF. But it doesn't really matter because we throw in an m as just kind of this constant that gets rid of everything, right? Okay, and so if I just plot this, type equals L. Did I do this wrong? Oh, I want x versus the PDF. What's going on? Okay. Okay, so this is what we have here. Oops, no, don't want that. All right, so we've got this, and then and so what we want to do is we just want to we're going to just do we're going to compare. We're going to propose values from, let's say, uniform. Okay, so I'm going to say y is going to be our uniform. I just want one value here. Okay. And I just say, okay, well, what is y? Y is 0.8321. Okay, so that shows up over here. And we say, okay, well, what is f of y? Okay, f of y is 0.373. Okay, and then so it appears like if I use an m of 0.5, okay, then everything between the ratio of m times g of x is always going to be taller than this, right? So my so I can do, you know, AB line horizontal is equal to 0.5 here. Okay. Okay, so I'm going to just propose between on the uniform from 0 to 1, and I got 0.83, and then so I say, well, should I accept this, yes or no? Okay. Well, what I do is I just do f of y divided by g of y. For the uniform distribution, g of y is just 1 for everything, multiplied by the constant, so I'm just going to divide this by 0.5. Okay? And so I would accept this with probability 0.747. So let me just show you where AB line of y is. This shows up right here. So this says, you know, this looks about 75% of the way up. And so we're going to accept this if, so I just draw another uniform. I say u comes from R unif 1. And if u is less than this, we accept it. It's 0.9, so we reject it. Okay? U ended up over here. All right? So I can just repeat this over and over and over again. I can just say, we'll do I in 1 through 1,000. Okay? And each time I'm going to generate a y. Okay? Each time I'm going to calculate my ratio, which is f of y divided by g of y. In my case, g of y is 1, so I guess I can say 0.5 times 1, which is g of y. So this is my ratio. And then I generate a u. and then I say if u is less than or equal to the ratio, then we will accept y. So we'll create a vector called samples, and right now this will just be this is terrible coding here. All right. So okay. So if u is less than the ratio, we will say, okay, we're going to just store samples, and we'll take our current set of samples and attach y to it. All right. Does this make sense? So I'm just generating an empty vector called samples. I'm going to generate a y between 0 and 1 here in my proposal distribution. In my proposal distribution, which is the uniform. We will calculate the ratio between f, which is this thing, and m times g of y, which is the line up here. And that's our ratio. And then we generate another u. And if that's shorter than our ratio, we accept it. Otherwise, we throw it away. Okay, so if u is less than the ratio, samples will be, we will append that value, the proposed value. That's our proposed value. This is our acceptance ratio. And this is kind of just, do we accept? Yes, do we accept? And this is kind of the random thing. All right. So we'll go ahead and do this. So I'm proposing 1,000 values. Not all 1,000 of them will get accepted. So we do this. All right, I'm done. How many values did I accept? What is my length of samples? Okay, I accepted 808 of these, and let's just take a look. Histogram of my samples. Let's do breaks equals 25, so we get a little bit of. So it doesn't quite look like a semicircle, but here's 808 values drawn from here. Let me see if this looks better if I do 10,000. So we're going to just clear this out. So it looks a little bit better, yeah. Maybe if I do breaks equals, I don't know, 40. It's starting to look semicircle-ish. We'll do 100,000. It's running. Again, because this is like the worst kind of code you can write, yeah. Yes?
So you want to use this in place of something like Riemann sums if the function is discontinuous?
So Riemann sums work for calculating integral, but here we're trying to generate random values from some proposed distribution where we know the PDF, but we don't know how to draw samples from it. Okay, so here I accepted 78, 619, and there's our histogram of that. That looks pretty good, right? So again, we're just proposing values from the uniform from 0 to 1. We create a ratio, and then we accept them with this thing. Okay. All right, we'll end here, and I hope you guys get started on the homework so you guys can ask questions appropriately. All right.